Welcome to the class on E540 Advanced Electromagnetic Field Theory and Antennas. I am Professor Rakesh Singh Satunam. This is the third lecture I am taking on this course. The first topic we will be discussing is called time harmonic fields. So in electromagnetic field theory, by default we assume all the fields are time harmonic fields. By the way, what is this time harmonic fields? So let us look into it. So for the time harmonic fields, we can separate the space and time dependence as follows. Let's say F vector is either electric field or magnetic field. Then it will be dependent on both space and time. So space dependence is with respect to variable x, y, z. Time dependence is with respect to variable t. So for the time harmonic fields, I can separate space and time dependence as f as a function of x, y, z, and time dependence can be represented by exponential j omega t. So now omega here is the angular frequency of the time varying fields. So now because of this time dependence of time harmonic fields in the form exponential j omega t, many of the differential and integral operation with time harmonic fields becomes quite easy. For example, if I consider the time derivative of time harmonic fields, let's say I want to do time derivative of the function f, which is a function of x, y, z and t. I do the partial derivative with respect to time. Then since this function is a product of two functions, one is dependent on space, another is dependent on time. Space dependence is simply f function of x, y, z. Time dependence is exponential j omega t. So when I do partial derivative, space dependence can be taken out. The partial derivative will be with respect to the time dependent term exponential j omega t, which is simply j omega exponential j omega t. So simply whenever I do the time derivative of time harmonic fields, is equivalent to multiplying j omega with the function itself. Similarly, when I do integration of this time harmonic field with respect to time, it will be similar to multiplying the function itself with j omega. How do we do that? If I want to integrate function f, which is a function of x, y, z and t, then I can represent it as a product of two functions. One is dependent on space, which is a function f x, y, z, and another which is dependent on time exponential j omega t. So the space dependent term can be taken outside the integration because this is independent of time. All I need to do is integration of exponential j omega t. So exponential of j omega t, from the vector analysis you know that is simply exponential of j omega t by j omega. We also have a constant integration c1, and we are interested in time varying fields, so we can take c1 as 0. So we can define dou by dou t as simply j omega, and we can also define dou square by dou t square. Double derivative of with respect to time is simply j omega into j omega is equal to minus omega square. So now for such kind of time harmonic fields, I can even modify the Maxwell equations and suppress the time dependence completely, and such kind of Maxwell equation is called Maxwell equations in phasor form. So what is this Maxwell equation in phasor form? Let us look into it closely. So now in this, all the time dependence has been suppressed, and we replace all the partial derivative with respect to time dou by dou t by j omega. So let's look at the four Maxwell equations for the time harmonic fields, which is also called as Maxwell equations in phasor form. So the first equation is divergence of D is equal to rho B. What we can observe is that D is no longer represented with an arrowhead. It has been represented with a tilde head. These are actually representation for the time harmonic fields, and this equation is called first Maxwell equation in phasor form. Second Maxwell equation in phasor form is divergence of D is equal to 0. The third Maxwell equation in phasor form is curl of H is equal to j omega d plus j. So now looking back at the Maxwell equation, we have curl of H is equal to dou d by dou t plus j. Dou d by dou t is the displacement current density, which is a contribution of the Maxwell himself, and j is the conduction current, which comes from the Ampere's circuitry law. So now dou d by dou t can be replaced by j omega d. So all the time derivative dou by dou t has been replaced by j omega. Similarly, we also have the Maxwell equation, which is Faraday's law's curl of E is equal to minus dou V by dou T. So dou by dou T, you replace it by j omega. What you have is curl of E is equal to minus j omega B. So these are the four Maxwell equations in phasor form for time harmonic fields. Actually, there is one very important concept which is called vector potential, which we usually use in antenna analysis. In the antenna analysis, what we do is from the current density, we want to find the fields everywhere in space. So this one observation is that finding the fields directly from the current density is a tedious and complex and lengthy calculation. Is there a simpler way of doing it? By using the vector potential, we can do it. Remember, in your electrostatics, we usually find electric field as negative gradient of electric potential. It was quite easier. Why it was easier? It's because electric potential is a scalar quantity, electric field is a vector quantity. Finding a scalar quantity, electric potential is quite easier. So now you take negative gradient of electric potential, you get that vector electric field. So now along the similar line, we will be using vector potential for finding electric field and magnetic field from the current density. First find the magnetic vector potential, then find the electric field and magnetic field. Why is it easier? So now here what we can observe is that magnetic vector potential, vector A, is a vector quantity, electric field is also vector quantity, magnetic field is also vector quantity. All three of them are vector quantity. So it would be difficult to find all these vector quantities. Then why we are saying that it's easier to find magnetic vector potential from finding electric field and magnetic field? That will be clear from the next equation we are considering here. What this equation we have for the magnetic vector potential A, and you can find it from the current density J. So looking at the equation in the right hand side, the only vector quantity we have in this equation is J. J is the current density. What is the interpretation? What is the interpretation of this equation? It says that J and A are having the same direction. So that means once you know the current density direction, you know the direction of A. So finding A, once you know the direction, is almost like finding a scalar quantity, because you already know the direction of that vector quantity, so it's easier. So finding A from J is easier because you know the direction of A follows the direction of current density. So now once you have the A magnetic vector potential, you can find the fields easily. We will discuss that in the following slides. So now again, this is one example I usually give in the class, you know, how difficult it is to find E and H from J directly, but it's always easier to take a detour. Instead of finding E and H directly, you find A first, then from A you find E and H. That's an easier task. An analogy I usually give in the class: let's say I want to go from point A to point B, but in order to go from point A to point B, I need to cross 3 hills. So I need to go up the first hill, come down, then go up, climb the hill, then come down, then climb the hill, then come down. So then I will reach point B. So this is a very difficult task. Very difficult to go up the hills and come down, then again go up the hills, come down, go up the hill and come down. So there is another simpler way of doing that. So instead of going A to B directly, you go a detour. You go to point C, which is in the plane area. It's a completely plane area, very easy to go. So from that point C, you go to point B, which is also a plane area. So definitely the first task is difficult task, second one is easier task. So it's exactly similar when you find out E and H directly from J. Instead of that, you find out A, which is easy, then from A you find E and H, which is also easy. So this is the two ways of finding the fields. We'll also take the second way, which is the easier way. By the way, so how do we find this E and H, or vector E and H, from the magnetic vector potential once I have A? We already know that I can find A from J, and we already discussed that. So once I have A, how do I find E and H? That's what we're going to discuss in the following slides. Yeah, so whenever you want to find some solution in electromagnetic field theory, you always use the Maxwell equations. Here also it's not an exception. So I use the Maxwell equation. This is the second Maxwell equations. The divergence of B is equal to 0. But from vector analysis, I also know that divergence of curl of any vector A is also equal to 0. You equate these two equations, you get B is equal to curl of A. So if you want to find magnetic flux density, you just take curl of magnetic vector potential. From the B, you can find H. B is equal to mu H. So I can easily find H vector also from B. So let us summarize. If I want to find magnetic flux density, I just take curl of magnetic vector potential. I was also interested in finding the electric field. So I want to find the electric field. So again, I have to follow the Maxwell equation. This time I follow the Maxwell curl equation, which is the last Maxwell equation. Curl of E is equal to minus dou V by dou T. So what is curl of E is equal to minus dou V by dou T? I know what is B. B is curl of A. So I just replace it in the right hand side. This is what I have. So now I combine the terms in the left hand side and right hand side and can rewrite it as curl of E plus dou A by dou T is equal to 0. So now from vector analysis, I also know that curl of gradient of a scalar quantity V is always equal to 0. So now if I multiply minus on the left hand side and the right hand side, I have 0. So 0 into minus, you multiply minus, it doesn't make any difference. So left hand side, I can again rewrite this as curl of minus gradient of electric potential equal to 0. So now you compare these two equations, you can write for time varying fields, electric field is negative gradient of electric potential minus dou A by dou T. So now you know that for electrostatics, I find electric field as negative gradient of electric potential. You have a negative sign here. Why we are intentionally multiplying with a negative sign here is because you look at the electric field. Electric field is going from higher potential to lower potential. Electric field always go from higher potential to lower potential, but gradient always go from lower point to higher point. So they are in opposite direction. That's why we have a negative sign here. So electric field is negative gradient of electric potential. But for the time varying fields, we have one additional term we need to worry about. We cannot afford to forget this additional term when we are considering the time harmonic fields. Electric field is no longer negative gradient of electric potential. We have one additional term which is called minus dou A by dou T. So electric field can be found out from the negative gradient of the electric potential as well as negative of the time derivative of the magnetic vector potential. So now let us summarize what we have learned in this class. First thing was time harmonic fields. Time harmonic fields have time dependence in the form of exponential j omega t. So because of this, I can replace the time derivative of time harmonic fields by j omega. So whenever I do time derivative of any time harmonic fields, I simply multiply j omega with the function itself. Similarly, whenever I do integration of time harmonic fields with respect to time, I simply multiply by 1 by j omega with the function itself. Then I have introduced you to the concept of magnetic vector potential. So in antenna analysis, I want to find electric field and magnetic field everywhere due to a current source. And it was very difficult to find electric field and magnetic field from the current source, but instead of finding electric field and magnetic field directly from the current source, I take a detour. I first find the magnetic vector potential which has same direction with the electric current density. Once I have the magnetic vector potential, I actually find the electric field and magnetic field. Magnetic flux density is simply curl of A, and electric field is simply negative gradient of electric potential minus dou A by dou T. That's all for this class. Hope to see you in the next class. Thank you.